So the first 2 days we do basic segmentation, manual segmentation, and some advanced segmentation already. Today we will focus on mostly the new advanced stuff. So it's called extension. So as you see so far on the previous 2 days, we did just the core segmentation or the module that we use. But today we're gonna focus on how you can use these packages called extension. So for example, you want to do fiber tracing. You would like to compute the porosity using for network modeling, or do matching, and also we focus as well on the deep learning module. Okay, and yeah, I think we can just start. I think not many people coming today anyway. So let's start with deep learning because it's still new, and then we can discuss about it. In Avizo, we implement deep learning since 2020, and the latest version since 2022 version, we already implement the new deep learning training model in 3D. So classically, we have the 2D training. That means you have the 2D images and you train on the 2D patch images. So the first thing first, before we do any deep learning, we need to set up the Python environment. So if you open Avizo software and go to project workroom in this setting here, to set up Python environment, you can go to on the menu here, and you can see on the top there's Python. Just click on Python, and there is the list that you can select an environment. Usually, if you create some environment, you can just select which environment that you can be used. So usually you can see here on my screen, I created a lot of the environment for a different version, but you can also create new environment as well. And probably all of you by default, you have this embed Python environment. So what the difference? Because usually what we did so far in segmentation workroom and all the recipe designer workroom, everything they just use embedded Python environment. But now for the deep learning part, we need to select the corresponding Python environment that used for deep learning. So we have a specific one. So for example, now I select deep learning 2022, and to create this new environment, just go to this tab Python, select environment, and create new environment. And then when you click create new environment, you can see that you can have this screen coming up. Just for example, deep learning. And I put the 2022.2 version, just so you know that which version and Python environment that are compatible with. Usually, yeah, the latest one should be okay. Yes. And it's important that when you create the deep learning environment, the Python environment for deep learning, you need to install this package that include the TensorFlow. So this is very important, because if you don't check this, install the deep learning packages like TensorFlow, you will not be able to use this package, and then deep learning gonna fail. And that's it. And then you just click OK, and then they will start to run the deep learning environment installation in your package, and then you should have this environment appear here when you create it, but it's gonna take maybe a couple minutes to run or install the environment. And once you have the environment, you can just select, let's say for example, I go back to embedded environment. They ask you to restart the application to use this new embedded environment. So again, because I just switched back to the embedded one, so I have to select this, the new environment that corresponds to my Python deep learning. So close, and then restart it again to start using it. That's the pre-step before doing deep learning. Yes, just only one time. Only one time when you want to switch between the environment. So by default, it's embedded environment. But if you want to start using deep learning, you can switch to deep learning environment. And most of the Python package in standard workload can also use in deep learning environment as well. So sometimes when you run some module and then they ask like, yeah, this not support Python environment, so you can think about it might be because of the environment that you selected. But since I running from the first day already, I have chosen the deep learning environment for all the time, so it seems to be no problem with all the workload that I have. Just in case, because by default, I think if you didn't create any Python environment yet, it can be selected by embedded Python environment by default. So just you need to create it and then choose it. Take a while. Okay, then we will start doing deep learning. So we're gonna download the example in the folder that I share. It's on workshop. Actually, it's on the KAUST folder as well. Here we have deep learning. So I'll start with the membrane folder and just look at the tutorial folder. And here we have tutorial deep learning membrane version 2022.2. And we select the first image to start with, this the section 180-220. So it should rename it. Okay, I'll send it quickly. And just need to input this voxel size information if you need to. Otherwise, click OK. So just take a look on this data by attach auto slice. As you can see here, we have cryo-EM of the membrane structure and also some organelles structure as well, like ribosome and mitochondria. So if you go to different layer, you can see this. And this, of course, it will be difficult to really do any automatic segmentation. And that's why we're going to use deep learning. And for deep learning, you need a very good graph truth that we explained a bit yesterday on the AI-assisted segmentation. But even then, with that AI-assisted, maybe you need to improve the segmentation for a while until you get a really nice graph truth image. So in terms of the deep learning, so we implement 2 steps in Avizo software. So first, we need to do the training step. So we call deep learning training. And in deep learning training, we're going to have 2 options, 2D or 3D. So let me show you quickly before we go into detail. So I will right click on this data. And if you type DL, you can see that they are available of 2 modules. So it's the deep learning training module. And you can select to do segmentation in 2D or 3D. So 3D is the newest version, but the 2D is already implemented and it works pretty well. So we'll start with the 2D first. And yes, as the name suggested, when we do this training with 2D, they will kind of create patch. For example, you have created patch of 3 by 3 pixels. This patch will go through all the images that you are setting, and then they integrate with the CNN convolutional neural network, and then go to this layer to compute the deep learning training to generate the model, the architecture model of the training. But we can go in more detail later. So, and after you finish this deep learning training, okay, I create quickly just to give you visual understanding DL. For example, I start with deep learning training in 2D. And once you finish the training in 2D, you will get 2 files, or 3 files, but the main 2 files is one is architecture file, and the second one is weight file. So these 2 files, you can use it as the input for the next step. It's called prediction. So after you finish that, I'm gonna do prediction. So we have to select deep learning prediction. And in this prediction, we have only 1 option, so we don't have the other option. As you can see here, in training step, we do only segmentation of the training, but in prediction, you will get the result from the training step. But also in the next, after we finish this training, I can show you that you can also use pre-trained model that we provided called denoising. So we don't have denoising training, and we cannot do any kind of other training because we only do segmentation training. because your colleague asked me about, for example, you want to do clustering training. We don't have this. You have only training on the segmentation. But for prediction, if you have architecture file or the model that you provide it somewhere else, or you get it something in the same network like unit network, we can try to bring this architecture file and do prediction. For example, we provide from Avizo, we provided a denoiser for EM membrane image, so you can use this as a denoiser for prediction. Okay, let's go into more detail. So let's start from preparing the image for the first step for deep learning training in 2D. So I have the original image here, as you can see on the right side. I will load the segmented image. It's called ground truth image. So I have to look in the same folder. Let's say I'll start with this one, membrane image. When I look quickly on this membrane segmented, it looks like this. So it have different ID for each layer. So you can see the membrane actually have one value, the same like a white membrane, but the compartment of the cell, they have different ID, so they have different materials. So if I overlay them, this is the segmented ground truth into original data using ColorWatch again, like this. You can see that the membrane are only one label, one structure, but the compartment, they have different IDs. So for the first time, we're gonna do training just only to predict the membrane. Okay, to do that, I need to extract this membrane part from this ground truth image. And for your information, this ground truth image has been segmented manually. I am not certain if they do kind of manual drawing control on each slide. So you have to draw it slide by slide and annotate them. So it's gonna take a while to do this. But this way you can get the most accurate ground truth image. And then it's very important because you cannot expect to just roughly paint it and to expect the precise result from the not so good ground truth image. So the precise ground truth image is the must to be able to predict the good result. Okay. Then I'll start with this ground truth first, just to tell you how to extract this layer, because I'm gonna train the first time using only the membrane information, not all the compartment information. So I will use arithmetic to extract this membrane. If I zoom in quickly, and remember that we have this probe tool to probe the intensity or the ID of this layer. So I click for update, and then if I click over here, and you can see this value of 168 for the membrane. So I will use this value to extract only the membrane pixel. So this pixel that have value of 168 will be extracted using arithmetic. So attach arithmetic to this membrane, arithmetics, and I select the result channel. Instead of like input A, change it to one value label image, because you can see here is grayscale image. And when I extract them, I want to convert them from grayscale to label image. Or you can just use like input A, and then you can do thresholding later, but it's just to skip one step. So just select one value label and use the expression A equal 168 that I get it from previous probing, and click apply. And what you can see here, after you extract the grayscale using arithmetics, I only get this information here. So that means I extract only one class of membrane to be trained using as the input ground truth image. Is any question so far at this step? So just quick again to summarize. So we have this original image, and if I overlay from ground truth, original ground truth, I have this one, but there's too many materials or many class to segment. So I just want to get only one class of segmentation. So I extract them using arithmetic. Just select this layer 168, and then you can see that actually I have only one ground truth of the membrane only. And then I'm gonna train this object in the membrane. And for this tutorial, we don't have the other new data set. So what we're gonna do, we're gonna use a small subset of the image for training, and because we want to test the training by usually you test on the new images, but because we don't have the new images, so we can do training on sub volume over here, and then when we get the model from the training architecture file, we can apply it to the full image later. So they're gonna interpret the full image as a new image. Okay. I just put the original image on the left side and this membrane ground truth as well on the right side, so you can get some overview. As I mentioned, that I will start to prepare a small subvolume of these images. So I will use the extract subvolume, and again, to have the same dimension of your image. So you need to use the region of interest or array box. Here I add an array box, and then I just select maybe a quarter of volume like this. This is the region of the input image that I subtract to get to the model to train, and they will train only inside of this image. And after we finish, we get architecture file and image file, and then we can start to predict the rest of the image in the full image. Okay, and then next I will do the extract subvolume to extract the same this region of interest. So attach the extract subvolume to the first image. Extract subvolume 1, and then link the region of interest to our box here. And again, I do the same thing for the result, the membrane, both of them here, and then link the extract of the ROI box to the region of interest here. All right. So now both of the grayscale and the segmented data have linked to this white box, and then you just click apply for both extract subvolume. I also unlink this from here like this. And now if I visualize only the result from extract subvolume, you can see here the ground truth label image has been extracted only this region. The same for the original image also been extracted here. So this two input image. I'm gonna start with the deep learning training, and also go to different slides just to see that what we obtain for deep learning training. Okay. So to start training, I will just go to this grayscale image, original one, and attach DL deep learning training segmentation 2D. So segmentation 2D, they will create hash. For example, in this image, is you look at information here is about 306 pixel by 252 in X and Y is the pixel. So we can create smaller patch like 128 pixel patch, and this patch will run through this image in iteration to complete the cycle. And one cycle we call one epoch, and number of epoch you can define them in this parameter. Look at the deep learning training module that we just generate here. So deep learning training segmentation 2D. And first thing we need to do, we need to input the image. Bring it up a bit so you can see. So from the input X, so we have this grayscale as the input X here. And then we need to define the input, the target Y. So that means we want to have this as a target of training. So then we need just to select the target Y by select here, or just choose it from this drop-down menu. So I just want to have the target Y as a result from the ground truth image. Okay, and come to next step is the train and validation. So they have option that you can do tiling. This tiling means originally we have really large image like this, not really large, but I mean supposedly you have large image, and you don't have enough data, or you don't have enough. You have maybe one or two images to train, and it's not going to be good enough for training. So you have option to break this image into like tiling them. For example, here you can set how many files to be break from one images. So if you maybe set in 128, and you can break this image into 4 pieces, and then it's considered instead of one image, you have 4 extra images, and then this can increase the accuracy of training. So, but for this initial purpose, we don't do any tiling. And then for splitting, yes, I know the name sometimes it's misleading, but just concentrate on this train and validation. So by default, it's 0.75. This means in terms of image that we are put into this training model, 75% we use as the for training. So it's gonna be trained 75% of the images, and the rest 25% of the images gonna be used for for validation. So 75% for training and 25 for validation. Also, you can also look at this information here. You click on the question mark and try to look at it a bit. They can explain on the definition of each parameters. Okay, I can try go here. So here they explain about this deep learning training segmentation 2D, and you can see here they explain roughly what is the tiling, how you splitting, and shuffle is to how the order of sampling of the image, but like you don't have to fix the order, just randomly select any image to start begin to tie with. So just some explanation. Okay, I just browse it, minimize it for a while. And then come to this training segmentation at the model. So we have unit network, and we have 2 types actually. So this is the other one. We have unit network and generic unit. And the other thing here, we just created just to see that we be able to import the other models. Like you want to create your own autoencoder, and you create this model and import into Avizo. But as we discussed with the year and Abdel, that if you use the other model, for example, if you use this somewhere else, autoencoder, and the next step when we do prediction, it's going to be conflict with the model, because the prediction step we're going to use the model from the net anyway, that we don't have other model provided for prediction. So just have to keep in mind that it could be somehow interfere with your training. So by default, just use backbone unit. And number of class. So it depends on how many material you segmented. So in this example, I have 1 material to be segmented is membrane. So number of class should be 2. Why? Because they always consider the exterior as the 1 class. So if you specify only 1, you only train the exterior material, but you don't gonna train on this membrane. So you have to always +1. For example, you have 1 material to train, gonna be 2 classes. And if you have more material later, I'm gonna show you that if you have input 2 materials, and then the number of class will be 3 classes, something like this. And backbone, you can select LessNet 18. And again, if you have doubt, you can just have some consult on this documentary. Okay. And yeah, so go down to training results. So you have to select the output directory. So let's say I go to desktop and create new folder, and say EL 2D, deep learning 2D, and select folder. And then you need to create a model name. So usually when you create this name, we try to get all information of the parameter that you input for the first time, so you can see which parameter you will take in. For example, in terms of parameters, down here we have maximum number of epoch. So by default 25, we can try 100 epoch. And loss function dice metric I use score is okay. And optimization, as you prefer. You could try HGD, but most of our experience, Adam is also good as well. So stick with Adam. And learning rate, just 0.1 is okay, or sometimes you can increase to 0.5 and see which the efficiency of the training. So for example, here I will use that. I use training model with the 100 epoch. And LessNet here 18. So this kind of information that you can put in your name, file name, and as well when you come here later in terms of patch size. So I will choose patch size of 128 like this, and then so this would be the last one information. So 128 patch. So just to any kind of name that you can remember all the parameters you input it. Okay, and come down here with the pre-processing, just use default normalization score per sample. And we have option to do augmentation. So in terms of augmentation, just quickly explain a bit. So sometimes you have some image that the feature of prediction or training is not homogeneous. For example, in this image, you have mitochondria always on the top and on the left, but nothing on the bottom or on the right. And all the image that you have is always like this, that top left only, and you don't have anything on the right or bottom. So you could be suspicious that like how model gonna predict if you have image that have mitochondria on the right or bottom. So because maybe you don't know if the model gonna learn this pattern by heart, not understand the global feature of the structure. So you have to give them some other option. So this augmentation can come in play. So what they do is that this augmentation, when you check on it, you can start to replicate or duplicate or create a fake image. So for example, you can flip them horizontal, flip them vertical, or rotate, or even shear. So you create new images that you have the feature, like if you flip them, then you have more mitochondria on the right side, on the bottom side as well. So you give opportunity of all the possible feature that could be appear in your image. Otherwise, the model will not be completely trained by the true homogeneous data distribution inside your images. So that term of augmentation. So we don't use it right now because our data is quite okay without augmentation. And then come to patch size, as I mentioned already from the beginning, that so we start with this training method like this. So and the patch size is how you define number of pixel in X and Y, because now we train in 2D. So we just need to define patch size in 2D. So number of X and Y. And if yes, 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 you turn it on. Yeah.
Is it advised to augment the data every time you're going to do deep learning training, for example?
No, yeah, it's not, because like this you see that there is mitochondria everywhere. So but you have more like really repetitive pattern, because sometimes we have the data. In my experience, they're looking for membrane imagination of the IOM here, and it seems like they take image on one side. The imagination of the membrane is always on one side. On the other side, it's just inside of the membrane or inside of the cell, so you will not see anything. So you expect like if you take other image that have the other side, it would be able to be predicted. That's why you need to do augmentation. But with this thing, you just go around, it's quite distributed even. Yeah. Yeah. So it doesn't seem to look repetitive to us. You can see that if you go to different slides, and then they just they're everywhere. So they're not like stick only on the one side only, or just for one position for one cluster only. Then it could create kind of
It's advice also first.
Yeah.
To the image.
Yeah, exactly. And also, for example, if you have image always like just give example like this image. If you have mitochondria here and always somewhere around here, but always here, so then you cannot trust that the model is going to learn this feature by heart. So next time when you see the new image that the software doesn't see before, they just only remember by heart. Okay, they only try to predict only the feature that are in this region. That's why we have to give them the augmentation, creating the fake image by rotating, flipping, share, just to make sure that at least they understand the global feature of this mitochondria, but not that is not only just only on the top, it could be anywhere. Yes, and also yes, as the DJ and Abdel is here, so they both are deep learning experts. So if you need more information on how you really adjust, fine tune on this parameter, you can also consult him later. I know this is gonna be brief, showing how the deep learning platform in Avizo work, but in more detail, and there at the collab, they can help you. So if you have any question, don't hesitate to contact them later or me. So I have no problem at all. Next, we were at the augmentation, yes, and then yeah, cropping. For example, I will start with the image here with about, if you look at the size, it's about 300 times 250 pixels, and you just need to create patch. So yeah, we can try with 128. I know it sounds a lot for you, but just image is not that difficult. So we try a bigger patch size. So what they do, they're gonna create patch of 128 in X and Y, and then this patch gonna run through during a training process to extract the product in each original layer. And then you run this until you complete one cycle, and one cycle that all the data go through the training, that's called one epoch. And when I said all the data, you can imagine that actually we have 3D images, right? So we have about 30 slices, and once the patch go to each image, and they go to one slide, to second, and then total until they get to top to bottom, or 128 go around like in a raster scan, and then that finish complete the cycle. So one epoch, and then we said like we want to run this 100 times, 100 cycles, so you run 100 epoch. Then what else? Then we have to select the patch per image. So here we can select maybe 2 patch, let's say. And then you define the batch size by define the number of images per batch. So if I do 4, so that means batch size will be 8. So that means in this epoch we have iteration. So to run 8 batch to complete one cycle. And as you can see here, we use deep learning training segmentation 2D. That means even in the 2D images, but the way we segment or we split the patch to extract the train, we do only 2D, like move patch for each slide and go to next slide in a set direction like this. But then if you activate the deep learning training segmentation in 3D, we will have one more parameter that so you have to define the patch size in set depth as well. And also the tiling also have option that you can extract the image in the 3D volume, not just through only 2D plane. That's the difference. And the 3D training in 3D gonna be much longer and needs more memory, RAM memory resources, and also CPU resource as well. And this some of the ratios, so it's not very easy to explain, but I can look quickly here. So it is explained on how much of the image that you could, it's kind of programming languages that, so for example here, 0 and 0.2, 30.07, and 100/01 mean that 20% of the patches have no constraint, and then the 70% of patches constraint, and at least 30% of the mask, and 10% contain 100% of the mask. So yeah, this is what I discussed with the and out there, so they can also maybe explain to you in really detail what does it mean, this constraint or not constraint of the patch. So you can just leave it at the default, but if you would like to to change it, you can also try and also maybe discuss or consult with the cloud app. And you can leave the MAC patch overlapping at 0.3. So yeah, and in terms of monitoring, you can just leave it as this. And this TensorBoard, that's why when we install Python environment, we need to activate the TensorFlow. So we just check it on TensorBoard. And also early stopping, we can do it next step. But this early stopping means that we have to set the patience. For example, if I activate the early stopping and I set patient of 25, it means that when you run 100 epoch, you keep modeling the progress of the training, and is no new information is being trained, or if you can set the validation loss is the loss, the progress of the difference is become 0, like 0 here for 25 epochs, then the training will stop. Even you set like 200 epochs, but if the training progress it start become flatten, saturated, or start to converge, then it's no point to keep training to the full 200 epoch. You just stop it whenever they have at least 25 epoch that been steady. I will show you exactly what does it mean here. So I just do it first and click apply. And also it's important to have internet connection because we need to connect to the tensor board. So click apply. I'm gonna run quickly, and then in a few moments the tensor should activate it. So in the tensor board, so we just look for the Scala here. Click on Scala. So we come back to you later on why you cannot visualize any graph here, maybe because it's some option that Avizo detected. So you just select Scala value. You can see already they have two informations, the training accuracy and the loss function. You can see here, strange. Yes, okay. You can see that the training and the validation. So the orange curve presented the train model, the image that's used for training, that's 75%, and 25% of images we use for validation. And you can see that what we're looking here, we would like to get finally the curve of both accuracy, training accuracy, and the loss to be converged. That means they should be reached at maximum and stable. And what I said before about the early stopping, for example, if you have the flatten of the curve at the tensor board here, for example, if you continue like this for 25 epochs, and then they should do early stopping. Even you set for maybe 500 epoch, so you can set the viewer over here to have it. You can see here the number of epoch on the bottom. We have 100 epochs. And for example, if you start to set early stopping for 25 epochs, so if they start to flatten for continuous up to 25 epoch, the training will stop. Even you set 100, but if you get this converged by 50 epochs already, they might already stop after 75 epochs. So you don't have to complete other epochs. So, and the way you look at the tensor board here, you just want to get finally the training and the validation somehow really converged. If not, it's gonna indicate like if you have really swing the validation value, the blue curve from the training value, it's also telling you that we have this kind of overfitting. Overfitting means that actually the model, they remember the feature by heart. They just remember too specific. They remember everything specifically, like remember everything by heart. But when you give them the new images, they're not gonna remember or not gonna find the new feature. So maybe some good example about this, like if you have two students and you want to train them to do the exercise, so you give them exercise, and if the student just remember all the answer for each exercise, and then they give really good result, or you thought that the training is really good, but then when you get to the new exercise, but they didn't know before, and then because they remember everything by heart from the previous training exam, then when you go to the new result, they cannot do it because it's different from what they remember. That's how they remember everything by heart, and that's called overfitting in terms of the training. and the validation. That's why we have to be careful. When you look at the curve, if you have this blue of the trend of the validation quite swing, like maybe later you will see it. Like here, if you have really swing from the training value, that means it's overfitting, and it just remember by heart. So it's not gonna give you a good indication. And what we can see here that we have training accuracy about 0.6. That's not so good, but yeah, just only for lovely image to get the first glimpse of what we could do, but at least it's converged at a certain point. And so we have lost about 0.2, so we expect less, so we want to have it like down almost to 0 to have a good loss. So the good training would be high accuracy and very low or 0 loss as loss function. So now it's finished, and then I examine the folder that we just created. Desktop here. So you can see that when you finish the training, you will get, mostly you get 2 files, but here it's like a file that you can optimization file. So the important one is the JSON file. This is model or architecture file that we're gonna use in the next step. And we come together with the SDF5 file. This one is the weight file. So this two results that it been generated by this training segmentation 2D model, and we're gonna use in the next step. So that also comes to the next point, that what I was saying before. In terms of training, segmentation, we already provide segmentation training. But for prediction, you can also, if you obtain the architecture file model yourself, you can try to use it in the prediction. And we also provide the denoiser membrane denoiser file as well, so you can directly use it. But we don't have the module to train the denoiser. Okay. Any questions so far on this step? So now I'll just inactivate it, and then maybe forget about this, so I can remove it, Control N. And what I'm going to do now, for example, if I just load a new data set, supposedly a new data set like this, so it's the same data set, but this now it's going to be the new data set. Let's say this the other data set or test data set that I want to run the prediction on this data. Remember, because I extract only the quarter of this image, and now I want to run the full image. So I pretend that I have the new feature that the module doesn't see before. So what you could do, you just right click and select deep learning prediction. And this is much easier and much faster. So you need to select the architecture file. So we just click and locate it. The file that we generated before is in this folder. You can see that it's only one JSON file that we created before. And then open. And once it's open, it will link to this SDF5 file and the custom processing file, the PY here. You can see in the deep learning prediction like this. So everything is straightforward. You can just click apply. But before going that, as I mentioned before, remember when we do the training, segmentation training, and we use unit model variant. And this could be issue if you're gonna import your own model. You can do that. You can add the new model to the training. But for prediction, it's still based on the unit model. So yeah, I am not certain if you create a new model and then predict them with the unit, how it's going to be like. But you could try to use this customized by select tiling manual, and then we adjust some parameter on the tiling. It might help it with the different model. Okay, and then click apply. And here we get the results that I can color watch them and select overlay. So you can see that from the TensorFlow already that the accuracy is not so good, and the loss also not minimized yet. And if you go through all these steps, you can see there's some part here. You see that they kind of overfitting some as well. So like maybe they're not too specific. So then that's why we need to look at the folder here, and you can see that we have information. Okay, we run 100 box, and use lens and 128 patch and so on. So you can maybe come back and load the information and then collect them and to see which one it gives the best result in terms of training. Okay. And now I will continue with the training, the same thing, but I will just increase number of class. So let's go to this folder again. And sorry, deep learning membrane tutorials training membrane 2022. So I will load two of the ground truth image, so mitochondria and the membrane neuroglial chip, these two, and open them. Okay. And what you can see here, we have remember the same ground truth image that I loaded from previous step, this one. And I also load an extra one that mitochondria. So like this one. So now we're gonna create two class of materials. Then we need to do is we need to work on these two images together first. First, I need to attach a arithmetics and use the input B as the mitochondria. So I have input A as this membrane segmented and the mitochondria segmented as the input B. Okay, so input A and input B. Yes, this one. So these two input have been added to arithmetics like this. And then we need to have the expression. So it's a bit long, so I will go to this shortcut. So you can go to user guide and tutorial. Maybe it's deep learning already. So just a moment, getting started with deep learning. So here also the tutorial that I just showing you quickly how you can do this, and then explain about the tensor board a bit. So the next step is that what I'm going to do now, I'm looking for the formula to extract the information of two module. Preliminary training, we go to the next training. Yeah, so why? So I need to, sorry, I quickly look at the formula for yeah, okay, here. So I need to copy this formula, A equal 168 like before, but then we need to also mask them together with channel B. So plus 2 times to the A not equal 168 and times to the B value that's not 0. So I copy this one. Okay, and just leave it for a while, maybe you can see it. So again, set the port to one value label and click apply. So now I copy this one here, A equal 168 and this if expression, and the option, the result channel is one value output like before, and then click apply. So what you get from this expression that you will have this two materials segmented from the two ground truth image. So overlay them like this. So you see that membrane is material 1 and the mitochondria itself is material 2, darker blue. And now we gonna do this same step. We can just use white box to extract. Here, maybe we can do, let's say, half of this object here, and then do extracts subvolume. So I increase that size, extract subvolume. here and then link to the white box. The same for the results. I also link the extract cell volume to the white box as well. And actually in the white box, you can also, I just do it like this. Halfway. Okay. And then click apply extract cell volume. And now you get the new data subvolume to run the second training. So I maybe just go back here using the visualization. So this is the new training data that I'm going to begin with. So, and this time we're gonna use again the deep learning 2D as well, but then we can change some parameter. Example here, I use target Y to the result here. So this target X again, it's target X, and then target Y with the true tile membrane. And this time you can see that with the parameter I'm gonna input, I can use the same training and validation ratio at 6.075, the same unit network. But number of class now, because we have 2 materials, so 2 plus 1 become 3 classes. It's the same resonance. The output, you can use the same folder. Yeah. And train here, we can say like, because I'm gonna change to maybe 500 epochs and 256 patch, for example. So, and here for initialization, previous step, we didn't do that, but we could do it by click on initialization, and then you can load the file, the HDF file that generated from the previous step. So this one, the weight file for initialization, just select them. And pretty much the same parameter, you can increase the learning rate to 5, for example, 0.004. And yeah, you can also try augmentation, activate them and use default parameter. Then patch size 256 and number of patch 2 and 4. Yeah, exactly. And for example, now I will do early stopping, and I want to have tolerance at 50 epochs, minimum 0, and then you can see a difference from previous step and click apply. That's strange. So probably I think I wrote the right one. Oh yeah, I know why, because my bad, because I used weight file from 2 classes, but now I'm training 3 classes, so it's interfering, so I just inactivate it. Sorry. So yeah, click apply. Then we don't need the initialize weight files, because yeah, I train different classes. So now you get another tensor board, and you can refresh them, and you can see now the new parameter train and parameter. Here you can see on the red one and the light blue. Focus on the red and the light blue. Keep updating, and you can see that you should just go to a logarithmic scale, see if it's really converging. Yeah, and take maybe a couple seconds. Still training now, like 20 epochs. You can also see it here as well. Oh yeah, finished. So that's strange, because they should yes, okay, as you can see here, we have number of class, which is still on class 0. So actually we look on the wrong class. So as we have 2 features, so the membrane is class 1 and mitochondria, the dark blue here, is class 2. So we should look at the right class. So for accuracy, I just click on class 1, and that's that. Yeah, I think I did something wrong with the parameter, because they stopped at only 20.
Seems also that they have big level.
Yeah.
That's 0, that's 1.
Oh yes, but it should be like if I look on the summary, they should have everything, but they stop at 20 epochs. I wonder why. Or maybe I didn't put the right parameters. So maybe I just stop also the augmentation. Maybe I just 128 and undo augmentation. So quickly look at the tutorials to give correct parameters to have it run. So image per batch 4. Maximum number of, oh yes, so I didn't include the number epoch to 500. That's the mistake. That's why they stopped at only 25. I look at the here, the TensorFlow, they stop at 25 only. And I forgot to increase the number of epoch. It was 25, that's why I stopped there. That's what I was curious. And number image per batch 4, and yeah. And then there's 2, yeah, correct. So I run it again. So my bad.
Every time you run,
yeah,
one is
generated.
computed,
Yeah.
It doesn't take anything from the run before.
No.
Yeah,
exactly. So here, if I, yeah, they start to run. Yeah, and see, and then, yeah, it's still running. And if I close this, you can see that they run 9,500 epochs now of 500, and continuing like this.
So one question is,
yes,
kind of related. I see that all the models and everything, all the training is running very fast.
Yeah.
So do you need a high-end computer? Do you need like a really powerful one to run?
Yeah, at least we need some moderate new CPU like Core Intel Core i7 i9, and then at least like 3.5 gigahertz clock speed. But because of free deep learning, they had this something in the CPU to run over CPU. But most of the training they will run on the RAM memory, so you need also high number of RAM memory, like 128 gigabyte RAM memory. So it really depends on the RAM memory. But also, if you don't have good CPU, you have really old CPU that one core, and it's gonna kind of bottleneck. Even you have the high RAM memory, that but you have really limited of CPU, it's gonna be a bottleneck for the deep learning.
Does it tend to have a GPU?
Not really. Yeah. But yes, usually when you run Avizo, you also have this high specification already. So as long as you have the minimum requirement from deep learning, from Avizo software, so it will be fine running the deep learning. And as you can see here, it stopped at 240 because, yeah, because explain again, when early stopping, we said that, okay, if after 50 epochs and there's no change in terms of improving learning or loss, then they should stop. That's why when you look at the TensorBoard of the Scala here, you can see that it's become flat after 200 and 240. So after 50 consecutive epochs, that there's no change, they stop stopping. And here you can see that it must improve in terms of the learning accuracy. So you can see that it's 0.8, 80%, 86% accuracy before it's 65. And the same for the validation also. Yeah, because you can see the validation, it starts to swing at the bottom. You can look at each class, because here class 0 is the exterior. You just activate the class 1. You see class 1 is the membrane light blue. Class 1 is pretty okay because they seem to not really swing that much. But then you look at class 2, you will see that they pretty swing. Why? Because if you look actually on the segmentation of this class 2 is not really consistent. They have some part that not well segmented like here. That's why when you start training and you look at the TensorBoard, you can see this kind of overfitting or underfitting, that they don't remember the feature because they don't have enough ground truth to really, can really tell, because it's also mitochondria, but you don't segment them. That's why you generate this kind of error on the swing. And then when you average between class 1 and class 2, you get this kind of swing a bit. The same for loss function. If you look at the, I don't see loss. Oh yeah, box loss. So you have lost the overview of loss, and loss. You're supposed to see, okay, you can see that there are also some swing, but you can also smoothen them as well. And you can see this smooth of the curve. Even class 2 accuracy, you can also smooth them a bit to, like, original data is like this, and then you apply smooth to see if they really start to converge with the slider. So this is a brief how you can monitor TensorBoard to examine if your training is good enough. So if you remember from the first training, we have like 0.5.6 accuracy, so 60% accuracy. But then the last training, when we improve number of epochs and then some parameter, and then increase batch size, and also patch image and patch size as well, you can see the accuracy become 80% and loss become smaller. This also better in terms of training. So now I'm going to use this again to run the, yes. Yes, exactly. So if you have more data, it doesn't have to be bigger data, but you have more data. In this example, if you have the data like this, what you could do is, let me go back to the original data. For example, you have some data like this, and you have maybe more of them, because this data is very small actually, because we have only like 30 slides. But we cannot tell exactly how many slides you need, but the more the better. So for example, you have 30 data, 30 slides for this data, and you have another data that also segmented, maybe 50 of them. You can merge them together, so you can, because even in 3D volume, but if you stack on top of each other, it becomes one volume, and you can just learn it slide by slide in 2D anyway. So the same principle. Or instead of stacking them on top of each other and learn at the same time, you can train like this first model and use this initialize to use the weight from the previous training. So that's why I try to input this initializing here with the weight file, but because I did a mistake, because the first training I do only 2 class, and now it's 3 class, so it doesn't match. That's why it's kind of error. Yeah. But it should be at least some kind of same feature that you're looking at. Yeah, exactly. Yeah, but at least you have to have the same, when you do the training, you have the same dimension. I think you just crop them. Yeah, but yeah, technically it could be possible. At least if you want to look for the same kind of structural feature in your training. Yeah, exactly. So it's just only the parameter that you have to fine tune. Yeah, but in terms of input image, as long as you have good segmented image that have the feature that you're looking at and precisely segmented, then you're gonna get a better results. And now I'll just show you quickly on the training. So I just remove it again just to not get confused too much. So again, load the same data set, and now I run the new training from 3 classes. So deep learning prediction, and load this from desktop. And now you can see that the previous one is the 100 epochs, and then we're gonna run the second one is 500 with the bigger patch size. Because if you have bigger patch size, you get more information to give into the model to build the more accuracy of training. And then the load automatically correspondent the weight HDF5 file, and then click apply. Now what I get is auto slice created, and color watch. So like this, and you can see if move through the data, you can see why the class 2 had a little problem, because they not predicted pretty well in some of the region. Like here, you see that it's indicating that you see the swing on the TensorFlow of the class 2 prediction. And yes, that's how you can set up the training for segmentation, both 2D and 3D. And in 3D, it's not different from 2D, just to specify instead of 2D patch become a 3D patch, and it's gonna take much longer for, but the result better. And what I would like to show you here, I mentioned at the beginning, with the deep learning, we also have denoiser. And this image, for example, I load this image here. So this is also EM data is really noisy, like this. Because we don't have the training for the denoiser, but we already provide the model, we can load it on the extra library. And what we could do is just attach deep learning prediction, and you just load architecture file. This noiser, so this is the noiser, the JSON file, and then they just automatically load the corresponding weight file. You click apply, and you get the noise of this membrane like this. Yeah. So as you can see that we already provide one train model, but the rest could be something custom developed, or you can consult with DGN up there. You can do something for you to train, to create a model, to provide this kind of model. Another example as well, maybe you would be interested for you. I have this trained from the real data set. So maybe not this one. Job deep learning here. Okay. Here, so just the same principle. So we have this data, and you just use the deep learning prediction. So I can also do it one more time. So deep learning prediction, you can already just load already the model that you trained before, and pre-train, and this one, this architecture file, the model that we prepared, and then just run it, and then you just get the result quickly and quite accurately. So if you look at the original data, so we just manually paint. Actually, what we did is here I paint manually, just use a segmentation editor and use magic wand to draw, like so 67 slides, spend maybe a few hours to draw them, and then run deep learning 2D, and you should get quite decent result already from this training here. Yeah, just some part missing, but we all look not bad. Imagine if you have similar structure, and you can just spend one quality day to annotate it, and the rest you just find for 100 slides or 100 data set. Is that okay so far for this deep learning? Yes. Yes. Yeah. So for example, you have two image volume, you can just merge them, but to merge them, you have to have like same data. For example, you have here, and I open the data is here, like this. If you look onto maybe bounding box, bounding box here, and another one bounding box here, you can see that they are totally different. But what you could do, you could just use transform editor to bring them together, and Yeah. Yeah. So you have to be sure that all two of the data you see is the size is different. You have to be in the same size, same x, y dimension, and fixed voxel information as well. You have to be. You see here the voxel size is 7.08, and another one is 111. So it have to be same voxel size, same dimension. If not, you can just crop them, but at least the voxel size have to be the same. And here because it looks smaller because the voxel size is changed. So maybe I will change this one to 111. So I do crop editor here and change voxel size to 111 like this. So it should be the same voxel size, but the dimension is 10, but it's not the same, but you can still crop them. But at least you have the same voxel size. Yeah, if you have many data, you could. I think we could create a script, but I never. Yeah, I'm not sure if we have this to crop the data in the same size, same dimension. I'm not sure if we have the real module. We don't have it, but I just take a look quickly on the extra library. So I keep mentioning about this extra library. If you look on this page here called extra.amira-avizo.com, so you can select for look for some many tutorial. For example, if you go to deep learning, you can search for some example how to start to do some deep learning exact hash size. Maybe this could be the question that you ask. So for example, you look at here and then they generate the patch. And even here they look at the pullback artifact. So actually they generate to create. No, this one is not what you asking, but it's more like the previous tutorial I showed yesterday that you create patch in different region and then you segment in each patch on the pullback. So you don't have to segment the whole image. You just segment only some region using this patch. So now we have automated in segmentation workload already. I will take a look if we have something that we can do the extract kind of image, but otherwise we can discuss with the people that if we could have the tool to best, yeah, extract volume, extract label. Yeah, I think so far it doesn't come to my knowledge. And here, sorry, your question yesterday about like how would you define length between the two objects. So for example, you create ambient occlusion and this label image, and then you can run this the length distribution along this label image, so you can measure the distribution or average distribution. So that's possible. That's what I try to explain about this extra library. Is really useful library, so you can search for many things. Okay, I think that's all for deep learning, and it's quite a lot to digest. But yeah, just keep in mind we have two experts here to help you in the future. Maybe let's take a break for maybe 10 minutes. So while waiting, I'm just gonna show you quickly the 3D deep learning result. Okay, so these are examples of the fiber yarn extraction. We do segmentation using deep learning. And so the grayscale image on top is original data. And at the bottom, you can see on the left side here is the 3D deep learning training segmentation, and this 2D deep learning segmentation. You can see already the quality of the 3D training is much better. It's more correlated to what you see in the real data. And even better if you just add a clipping plane to visualize this. Clipping plane. here. Yeah. So I'm just showing quickly the result comparison between deep learning of the 3D training and 2D training. So on the left is 3D, and on the right here is 2D training. So you can see that the 3D training get a more precise results compared to the original one. I mean, like compared to the 2D training, and it looks more better than what we have in the 2D training. So I hope you get some idea what you can expect from better quality of the 3D training. Okay. So then we'll move to the new section on. Yes.
So 2D, we had to prepare the training.
Yes.
And we did it by segmenting our hands.
Yeah.
With a pen or with a mouse. And yesterday we tried to segment 3D for like interpolation.
Exactly.
And it was not precise.
Yeah. But what you could do from yesterday, you could do, okay, I load the data one more time from yesterday. This one, and I can explain to you. So yeah, even it's not precise, but you can do like clean up. So I load this project here. One for this mitochondria here, like, or let's say the filament. So if you use this AI assisted to extract it, what you could do, you can clean up, for example, remove this small spot here, and later you can also, whatever here the missing wedge, you can also maybe use manual to connect them to make it complete. This is how you kind of finish up with the deep learning training. Or even here, you don't have to use the full volume. You can maybe extract only the good part and use as an input raw truth image. That's a
yeah, but still it's 2D.
Yeah.
Do you remember the sneakers bar, which we did like the chocolate from the one side, the chocolate from another side?
Yeah.
And then we interpolated, and this is how we three-dimensional segmented.
Exactly. Yeah. But that
but it was not precise.
Not
for
precise.
Example, I want to make it precise.
Yeah.
To train my model.
Yeah.
Because the precision here is crucial.
Exactly. So what you could do, you have to do mostly manual. So if it goes to segmentation, and for example, if you look at the this image here, so no problem. So now I need a new 3D segmentation. Anyway, I'll go here, and you want to really precisely, you can use maybe go here. Some special tool like we have this magic wand here. You can use the, for example, auto trace, and you can try to trace them. You can see here, like here, how do you, okay, let's go back one more time. Just zoom in a bit like this. So this just example how you can use the magic wand. So I go to magic wand, auto trace, and you can see I can use this kind of freehand, try to follow some structure here like this. So this is, yeah, you're gonna spend some time kind of painting them like this. I hope you can imagine like how you can precisely draw your object. And here you cannot use interpolation because you have to do it slide by slide. Imagine you have like 100 slides, so you have to draw every slide by hand like this to get really precise. But it could worth it if you have very precise graph to. So finally, if I like this is more like manually drawing, and have to be side by side. With the interpolation, it's not gonna work because
So for example, here I have 80 slides, and if this feature goes through all the 80 slides, I should go each slide by slide.
Exactly like this, and then you go to next slide and do the same again. Then no interpolation. Yeah. Okay, then let's move to the next section. So I'm gonna focus on the extension. Extension means usually here we have the standard package. You can just use module, but we have special extension for several things we could do. So start with the core network modeling. So I will just load qualitative data. So it's just on the folder C program file and go to Avizo 2022.2 data, and it's PNM tutorials, and then PNM, so it stands for Paul Network Modeling. Okay, so we just load the raw data, sponsorum.am, and take a look quickly on the volume here. And every time if you don't see them, just assume that you need to click on view all. And you have here this foam bubbles here, and the aim of this network modeling, we want to study the connectivity between this pore space inside of this material. You can see that the pores and have different pore size, and the connectivity we control between the pore. So okay, let's start it. We need to do some segmentation of the pore space, and after that we're gonna connect them by select exit connectivity and then start to calculate network model. Okay, so let's start it. I quickly used, let's say, you can, as a precaution, just use medium filter to clean up a little bit noise here. So after filter, we can get quite better image quality. So before was here, and then I enhanced by remove noise a bit, and then you get something like this. But it's not really crucial, but I didn't do. So next step is just threshold them. For example, I will do auto thresholding and click apply. And I just remove this info table, become wrong button. And just look at the threshold results. Actually, we want to threshold the pore space, because when I use auto thresholding, I didn't select auto threshold low, with by default auto threshold high. And just I want to show you another function as well. So that's why. So when I do this auto thresholding, I get only the white foam space, but not pore space. So I would like to invert them. So just invert it to the pore space as a binary image. After inverted, you should get this pore space like this. Okay, just nothing complicated, just to show you some other features that we have. And visualize the pore space in 3D volume. It look like this, all the pore. And if you overlay them with original data, look like this. So maybe here, and yeah, that's okay. Avizo also have some issue that when you overlay two volume together, the rendering it become strange. And you can see here when the quality is dropped, not realistic anymore. So anyway, you can see that the gray one is the foam mass, and the blue is a pore space that we've been extract using auto thresholding and invert the gray mass into the pore space. Okay, and then from this we gonna do axis connectivity. So now we do attach axis connectivity. With axis connectivity for pore network modeling purpose, so we're gonna select the least neighborhood, because usually in terms of interpolation, we always not interpolation, the interpretation of the neighboring box. So we try to use maximum, but for PNM, try to use the least, the 6. Only the face to face, so we want to limit the result of the connected between the voxels. So orientation in set is okay, or in any direction. So after you have this exit connectivity, you can already see from the preview that the small object had been removed. Oh no, sorry, the non-connected pore space will be removed. So from here, you can see that this is all the pores. But after you apply axis connectivity and look at the pore space that are already interconnected to each other. So this black dot are non-connected pores. So we just remove it because we want to study only the connectivity between the pores. Okay. That's why we do this axis connectivity. The same if you look at the volume before axis connectivity and after axis connectivity. So we remove unconnected pore from this object. And then I will separate them into individual pore because we still have only one material. So apply separate objects, which is the watershed segmentation anyway, and use the same marker extent of 2 and 3D space, and just select the output as connected objects like this. So 3D marker extent 2 connected object and apply. Exactly. Now you can get object separated here. You can also, for example, here to calculate volume fraction of your connected pore space in relative to the full volume or the full mass as well. So you can, as for example, volume fraction, and then you select input image mask. Would be, let's say this, not this one, the invert here. So you could try to get the volume fraction of this pore space here. Yeah, just an example, but it's not crucial to do this. Just if you would like to have the volume fraction. And now come to the last part of this pore network modeling. After you prepare this data, you will get the final pore that connected and each of them separated into individual pore. So maybe I could reduce the separate object criterion, but there are some objects still separated, not separated well. So I reduce marker extent to 1 to have more objects separated. Yeah, so that's the maximum we could do. So everything else separated. And even here it's not good enough because they've been somehow separated. But anyway. Okay, at this point, we're gonna attach generate pore network model to this prepare data, generate pore network model. And it's very simple. Actually, you can click apply, but you can also select to generate property as well. For example, you want to see the direction of flow in set direction, and you just input your boundary condition like input pressure is the 1300,000 Pascal, output pressure 10,000 Pascal, and then viscosity of your fluid to simulate them, and then click apply. Then you have some kind of warning that this you have so much throat and pore ratio, so just ignore it, just close it. And now we're gonna visualize.
Sorry, can we not ignore them? Can we take a look?
Yes, sure, of course. So they said 70% of the throat are unexpectedly detected smaller than the voxel size. So this means the connection between the two pore space could be not accurate because the voxel size, for example, you have one voxel size of 1 micrometer, but the pore space that you detect the throat, the channel, is smaller than it. That could be micro fracture.
But it's like 72%.
Yeah.
So if I do any simulation, flow simulation, absolute permeability simulation, doesn't mean that it's not correct at all.
Yes, I have to come back to you for it because it's due to also weak contact level because of the most effect. This contact may be produced in accurate measure. You are right. Please refer to the community for more detail. It's a precision. So yeah, I think we need to try to come up with in terms of I have to look on the voxel size. Probably we need to adjust the voxel size to become larger to have the correct voxel size, or at least to modify them to make it surely that it's going to be larger than the throat.
But this voxel size is the property of my image, right?
Yeah.
So if I do CT scan, the voxel size 3 micrometer, that's it.
Yeah, I understand completely. Yeah. So that's a good question. Yeah. So I have to come back to you on this for sure, because we didn't really consider much on this question, because I thought it's kind of warning, but you raised up good question. It's not going to be accurate in terms of calculation, so we have to really find out like what is the issue and how can we improve this error. Okay, thank you. Okay, and then we have the two results. So we have this result here of the pore and throat. And just let's take a look on the image first to understand. So to visualize the result, the properties here, or as well, you need to attach so-called a pore network model view. So you have this flooded, not the properties. So attach the pore network model view to the properties. So you can see here, and then in the pore network model view, you can start to play around with some parameter here. Start from pore and throat. And you can see here by section of pore, I can change the pore scale to, let's say, volume, and then expand by factor exactly like this. And you can change the coloring of the volume. Okay, let's say volume like this, and then you adjust this. So it's just they fit the sphere to equivalent of the volume of the pore space. That's why they call volume, but it's not the true volume. It's just a volume of equivalent sphere that fit into that pore space. And the same for throat. You can also change to maybe channel length to see which, and also factor. Not much. You can also do it like this, and also coloring you can also change as well to, let's say, channel length, the same thing. So you can estimate like which connectivity between this pore and the throat. And you can see now the bubbles, the sphere here represent the pore, and the channel length or the throat here is the tube is a throat. So, and you can see this information over here, the pore and the throat. We have, for example, the area, equivalent radius, channel length of pore, and the same for the throat, and then the same for the pore. We have volume 3D, so equivalent volume of the sphere that fit to the volume of the pore, and the area, equivalent radius, and this simulation that you put pressure and the location of this pore space, the center of mass actually here. And you can also change, for example, if you want to scale the pore to equivalent radius. I think it makes sense than the volume, so just select equivalent radius and then start to maybe scale it up and change color map of the pore itself. So it depends on really what you would like to visualize them. And then if you just overlay this to original data, see it here. So this represented only connected pore, and side is showing the equivalent radius, and you can see the throat, how the pore connected to the other space. And there's 3 here, there's no connection. That's why they only look for. And this property that we generated is also, we simulate the full flow probability inside of this channel for the throat. So, is that any question on this?
Do we have different shapes like
of the pore?
Pore and both ones?
No, we just only represent them by sphere and the cylinder. So we don't have other option, but you can just scale it up like Yeah, so you don't have the other shape, so it's a bit limited in terms of the visualization. So I go back here and then maybe change which is the opacity. So, yeah, so I think that's what we could visualize, but not everything. So pore space channel between the pore and the connectivity, and also the properties that you are simulating here. Okay, that's not really difficult. So, and we have this tutorial inside of the Avizo, so you can click and try to run. So for example, I go to this one here, open data. So you can see that you have this tutorial. You can click prepare data, open it. And then they already have prepared data prepared. You just need to click to run to generate pore network model. So they have even some additional volume fraction and calculation. And here you see that they have all the steps that I've done with some like extra step. But anyway, at the end, you just select to generate pore network model. And it seems to have all the error warning every time when you run it. The properties. So I will come back to you. What is the so actually that's why it's 0.7%. It is only 8%, so that's why it's really not 70%. Yeah, it's 8%. So the same warning. So I will come back to you on this question, and the rest is just have to visualize them.
Thinking maybe it was not 72, but maybe it was 0.72.
Yeah.
Less than 1%.
Yeah, exactly. That's 70%. Yeah, I was wrong on term interpretation because this one is 8%, previous is 0.7. Just very minimal, very small. Yeah. Okay. That pore network model. And similarly, we can also do simulation of the properties. So open data. This one we're going to use the extension called XLab. XLab is just to simulate the properties like thermal conductivity, permeability, and so on. So we're going to go to the data in the folder called to the XLab tutorials, I believe. Yes. So it's in here, XLab. So we need just to open the first data, the 200.vol.am, and take a look on to the full data set. Or here. So it's a bits, pack of bits. And now we want to sample like simulate the flow or permeability inside of the bits. So similarly, we need to do some axis connectivity as well, and to generate the label image. The first thing we do the auto thresholding again. And this time, yeah, I do the same thing, auto threshold low. You can see this. And from this, I need to create invert them. But we look at the pore space, exactly, pore space, invert them again. And then you just get exactly the same like we did before. So we look at the pore and how we gonna plot with the stimulation of the properties. So before we doing that, we need to create a small region of interest, because if you run the simulation on the full volume, it's gonna be too long, too much computation. So I will need just to create the Roy box. And maybe something not too big, just in the center. This, and then maybe only on the volume. So I'm trying to move it a bit. I don't remember the dimension by heart, so I have to just try to figure where would be just the center of, yeah. I think that should be enough to should do the job. So then, for example, now I just come back to the full volume and you attach the box here. This is where we're gonna start working on it. So we can do by extract subvolume and set the array box of extract subvolume to here. That should be enough. And then click apply. And this should be the one we will start working with the simulation on the properties. So I will go to permeability, yeah, absolute permeability experiment simulation. Just a bit long in terms of the name. Absolute probability experiment simulation. And in this property port here, you can see that they have option to select the value either 0 or 1 because we inverted of the label image. Remember we create this label image like this, and this label image before we from auto threshold before we inverted. The value of the pore space is 0, but because I inverted them, then now the pore space become value of 1. So then in absolute probability experiment simulation, so I have to change the pore space because I have to define which one is pore space, 0 material background or the 1. So but now the pore space is 1, so I change to 1. That's it. And the rest you just use the default parameter, and you can see that you can compute. By default they select CPU will be faster, and that's why we need to select only the small subdivision. Otherwise, it's gonna take a long time to run on the CPU. Yeah, and you can try to select on the advanced setting to see this. Yeah, but this is too complicated, so you can just use the default parameter for the time being and click apply. So they get some error. Yeah, not bad, but you see, like we see on the tensor board that we try to get if they start to become converge at some point. And then we get these results like this: pressure, velocity, and some spreadsheet. So to visualize the pressure, you just need to add height map slide. And this height map slide can display this pressure assert on certain region. And as you remember from yesterday, we can change this height map slide and adjust the scale and also offset of the height map slide like this. So you can see this representative of the pressure exert on certain region in different axis, Z and Y Z. And for velocity, so we need to compute the magnitude of the velocity. So select magnitude, and apply, and you get the magnitude of the velocity. And to visualize the velocity, just to have to go to this display and select illuminated streamlines, create, and you just connect the color field of the illuminated streamline to the magnitude that you just created. And now, in terms of the parameter setting, we need to set color map to physics and select number of lines that increase, maybe here, length, width, opacity, fade factor, step size, and then you can just select to create animation to animate them, the flow, and then also this to give the color and click apply. So you can see this here. You can also hide the tab box and you change number of line, length, width. It depends on what you would like to see, and also fade factor and step size. It seems to be width, opacity, fade factor, step size, speed, constant. Then no. It seems to be that I have yeah, maybe I have too low fade factor, and length maybe just goes a bit here, and yeah, it's just how to just adjust your step like this. And if you overlay these two subvolume of the original data, like this one, so you just see transparency here a bit like this, and adjust the can be the thickness. So you should see the absolute probability of this flow of velocity showing in the animated way. Is that okay so far with this XLab absolute probability and simulation? We go a bit, yeah. Because I use the combination of the color map physics and then I use the DC, so it also doesn't give meaning because I just use the combination. Can apply. You can see that I don't use this DC option. They don't have this color. Yeah, it's just more to visualize, but the color it doesn't correspond much of the property that I generated. And can say,
is it any way to check the code which is used here?
The code? You mean the module here, right?
The program which is running.
So I haven't checked this before, but just take a look. So they have some background information how they run, but I'm not sure if they really give you the code. But what you could do here, we have Python console. Yeah, could be. No, this is from deep learning. Yeah, probably. Yeah, I will get back to you on this question as well because I'm not sure if we really provide the code on this simulation. But I think we could give away because we also do a lot of collaboration. For example, like during the pandemic, we collaborate with the university in Belgium to simulate the flow inside of through the filter of the surgical mask. We want to create the reusable the mask. So you have the mask and you have the filter. So we want to simulate the flow of the air into this different type of filter, and you see which one you have the best capacity in terms of remove this virus particle and also to give a lot of airflow into this mask. So, and it could be something that would be useful for research. So I don't see the reason why we cannot give you the code.
Also, NMR simulation in Avizo.
Pardon?
Do you have NMR simulation here in Avizo?
I'm not sure.
Run a walk. You were searching through some folders and search yesterday.
Yeah. So we have if you go to this XLab folder here, so you can see that what we have here, we have absolute probability, molecular diffusivity, factor, electrical conductivity, and thermoconductivity. This helps simulation. But the rest, if you want to do simulation, then we can contact us. We can discuss about it. Could be something service project or something that we could help you with, some collaboration. Yeah. Okay, this simulation. Any questions on this? Yes. Yeah. Yeah, I understand, but I'm not sure because you can see here we have tab box. You can select you see tab, but if I crop them, that's first question I got it. And then click apply. Yeah, seem to okay, possible. You just to define the tab box where you want to visualize them, and if I again overlay. No, because this is inside the illuminated streamline, the display option, and inside there you have this box here. So it's where you can do this, because we have the LOI box over here that I didn't activate yet. This is the LOI box. Yeah, so it's like they have their own LOI box, and then you can adjust it. But even the LOI box is there. Yeah, they have something outside LOI box that's really strange. You can see. Anyway, but yeah, that's possible. Okay. And the next would be something different, because this core network and simulation would go together and then related to each other. So if you don't have any question on this, I'll just move on to the next one called XWin extension. So this XWin, we're gonna generate a 3D volume mesh. If you remember before, I was presenting the surface and then how to generate surface. Now we're gonna do 3D volume surface, and we need to load the corresponding data. It's also in tutorial folders again, and select matching, and let's select canal conf.labels here. It's already prepared, so if you visualize them, it's actually 3 materials. So they have soft endosperm, hard endosperm, and germ, and just use clipping plane to see inside. So it's been prepared from the original grayscale data. You can see 3 material inside. So soft endosperm, hard endosperm, and the germ part of the corn. And remember, before I did yesterday, or the first day we generate surface. So I show you quickly generate surface. And click apply. And you can see that surface that I created. I press the wrong button. I'll do one more time quickly. So if you look at the volume rendering, actually you have 3D volume, solid volume, and then if I generate surface, the surface that you see, it actually is a hollow surface like this. And if I click this surface, you can see that it's just 2D triangulated surface, not a 3D. So it just triangulated surface on 2D, and it's empty hollow inside. Okay. And what you're going to do now in this section of XWin, we're going to sorry. I'm going to create a 3D tetrahedral mesh. So we're gonna need help from the workroom called matching workroom here. So before we doing that, just remove the other results. We don't need. So we just have only this con.label.am, and then we go into the matching workroom here. Click on matching. So they have their own workroom. So look at the mesh panel on the side. So you can select mesh when one you generated, but at the moment we don't have any mesh. So what we need to do, we need to start to generate mesh. So look at the label data. So we load the con.labels, con.label.m. So this is the data we have. And in this label, we have 3 materials. We already defined as a hard endosperm, soft endosperm, and germ. Okay, and we get the information. So the first thing we could do is just do fast matching. This is very fast, and just to get an overview of the mesh we're gonna generate. So click create, and when you click create, you get this 3D mesh on the side, right side on the 3D mesh viewer. So you can click on each material just to hide them. For example, hide hard endosperm. You can see only the soft endosperm and the germ. You can also hide the germ or hide the soft endosperm and overlay them with hard endosperm. here and here you can see that this is kind of visualize the mesh. And just to give you a proof that it's a 3D mesh, then you can just activate on the right side here, clipping plane. It's a special clipping plane for the mesh. And you can see that mesh has been generated, the volume mesh of the 3D tetrahedral. So if you move this slide around, you can see that actually this 3D volume mesh. You can also change to the rotation of the clipping plane. You can see here the mesh that has been generated. Yes.
Some people usually use it.
Yes, that's a good question. So I deactivated. So what you could do that when you have the mesh here, you can export them for further like finite element analysis. And I'm not sure if you use finite element analysis or like fluid dynamic computation, but that
finite element analysis.
FE.
What did you say?
Yeah, you create the property and you generate some computation on the mesh. So you just generate it. For example, you want to create boundary condition for the mesh, and you export them into other solver. So as you can see here, the type of this exporting. So you can use, for example, like Abacus for solver for the finite element analysis, or you can use sometimes NSYS or Fluent. That's what people use, or console. But yeah, I'm also not the expert in the finite element analysis. But if you need to do this finite element analysis, then you can use this mesh to export the tetrahedral volume mesh into this solver here.
Can we use this mesh for simulation, which we did on the previous step?
No.
For absolute permeability.
Yeah, that's the difference. So this is a specific file that used for this type of the finite element analysis solver. So it's like yeah, Abacus NSYS. Yes, console. And also because yeah, I'm not sure about that, but you maybe custom created using this mesh, but what we could use this tetrahedral mesh not in simulation that we did before, but we can do for DVC, digital volume correlation, so that we can generate the mesh and then we can start to simulate the strain propagation or strain map, displacement map, strain map, and displacement map using the tetrahedral. So yeah, that's, for example, now we generate mesh, so you can select mesh and to export to any solver that's available here. Yeah, mostly Abacus, NSYS, console, Fluent that people use a lot. And okay, to go further, for example, now we use the fast matching. So, but then if you want to like do more stuff, so you can adjust the mesh. So for example, I increase the mesh quality from medium fast matching to a bit higher. You can see that when you use this parameter here, they just adjust the facet size, facet distance, and the cell size automatically. And then if you click create, you're gonna create a new mesh. But if you click replace, you're gonna replace the certain mesh. So far we have only one mesh. So if I click create with the higher resolution of the mesh quality created, and you can see that this new mesh is more better in terms of quality, but then they generate two files. Unless you want to, okay, I go back to the first mesh that's more close and maybe reduce the quality like this. And then now I replace it. So this one will be replaced with even coarser mesh. And you can switch between the two, like the first one and the second one. You can see how the mesh coming up. Okay. So, and in terms of the extra, for example, people want to create the boundary condition by, for example, look at the interface between the two layers like this. So you click on the boundary, and let's say I want to look at the contact phase. So if you just activate one of them like this, and then you can just select the contact phase between, let's say I want to highlight on hard endosperm, just click on the name here, and you can see that this is hard endosperm contact with germ, and it's only the two But you can also check to have, for example, if I have Sarawuth endosperm activated, you can see it where the contact interface between two, and so I can maybe select germ as well, like this, so you can see where the red boundary interface between the germ and the sub-endosperm. Also, you can add this boundary by, for example, now if you select this about the contact phase between the hard endosperm and germ, so you can just select surface and interface and add it. Yeah, and when you add it, you can just I visualize this one and select that. Just out of nowhere, just don't see it anymore. Yeah, okay. So if I, for example, like this, so you can see that if here is the one I selected, but the green membrane that is what the one I added before, and then I overlay this. What is boundary condition in the interface between two layers, and this boundary condition also can be added as well, and then export to this object. Also, this matching workloop is really for people who regularly using with matching, so you can just quickly generate by using this function fast matching, or if you want to define your match, you can also change number of facet size and use Scala information to define some different parameter to modify your match mode. But if you want to even go further advanced in terms of input, so what I could do here, you go back to project workroom when we have the module called generate data match. Generate data match. And you can see here, if you look at the advanced mode, we have even more function to control the quality of match, and you have also to get your knowledge on this matching. So, but I just stick on fast matching exactly the same like we did in the matching workroom. So fast matching, just everything by default, and you just select either very coarse, medium, fine, or very fine. So I just go to fine, for example, click apply. You also generate the same thing. You create tetrahedral match. But then to visualize in project view, you need to go to data grid view to visualize the match like this, and change the draw style to outline, and then you can see this. But this is not really interactive like in matching workloop because it's quite limited. We don't have specific clipping plane in the 3D viewer to view this match and so on. Yeah, it's pretty much about overview of matching. Yeah, is that okay so far on this quick matching? Okay, then let's go to the next one. It's also really powerful extension that people use it a lot, or X-fiber. So we're gonna do fiber tracing of the fibrous-like structures. So need to open the data for fiber tracing tutorial and look at the fiber tracing somewhere. So I still need some time to look because data strange because it should be right away here. Tutorial. Yeah, fiber tracing. Sometimes you miss it easily. So I just load the data concrete.am and look quickly on this concrete data like this. So a concrete fiber. So the aim here, we want to trace the center line of the concrete. So using the X-fiber extension. In this extension called X-fiber, we just apply two modules into this extension. So the first one is cylinder correlation. And after we do cylinder correlation, we're gonna do trace correlation line. Just go there into more detail. So the first thing we do, start with the first module, cylinder correlation. Cylinder correlation. You can see the name of the extension at the back in the bracket here. Cylinder correlation. So when I attach cylinder correlation module to concrete.am, and then we need to start to look at the parameter here. So first thing we need to do, we need to define the diameter of the fiber. So estimately, you can go to concrete.am, add auto slice like this one, and then try to look at one of the slide to show the representative fiber diameter. So let's go like here. And now I will start to measure them using the measure to the line. And I go maybe from here, this point here. And you can see the diameter is about 8, 9, or 10. It depends on the fiber that you choose to measure. So about from 8 to 10 micrometers. So that the estimately what we know about this fiber dimension. And next is look at this parameter input. So we need to input cylinder length, angular sampling, mass cylinder, and outer cylinder radius, inner cylinder radius, and contrast. So it easiest, the first thing you can see that contrast is bright on dark. But if you have the object that's dark on the bright background, so you can select dark on bright, but here it's just bright on dark. And from this in parameters here, everything here, we will start from the outer cylinder radius here. So as you can see here, we measure the diameter of 8 to 10. So I can input, let's say, outer cylinder radius to 4, because half of the diameter. And the next step is, once you get the outer cylinder radius determined, you can create a so-called mass cylinder radius, because the actual radius from the cylinder, we define them, but then we need to get them what is the maximum detection of the mass that you can give kind of threshold. So the value of the mass cylinder radius is about 1.2 to 1.5 times the outer cylinder radius. For example, if you have the outer cylinder radius of 4, so you can put input the mass cylinder radius about maybe 4.5 or 5, like this. And then angular sampling, it just how to like look for the contrast between 2 points. So usually you can just leave it at 5 because it's a good angular sampling. You can adjust it as well. And if you want to know more on the angular sampling, they have some information here. So orientation of the cylinder template that compute to cover half of the sphere to 5. But in general, we just leave it at 5 and then they will do the job. And then the next one will be cylinder length. So cylinder length, it could be about 4 to 5 times larger than the outer cylinder radius. So I input outer cylinder radius of 4. So 4 to 5, like 16 to 20 of the cylinder radius. That should be the optimum parameter. And because we're gonna create the fiber, solid fiber, not a hollow fiber, so you just leave the inner cylinder radius at 0. Unless you want to trace the hollow fiber, then you can input the inner cylinder radius by measure them and then just input it. And it's gonna run. But now I would like to show you like the easiest way to compute this parameter. So you can activate the visual cylinder here by select on visual cylinder activated. And when you activate it, you can see that they have their own auto slide coming up. So I delete this auto slide first and delete measurement. Go back to module cylinder correlation and look at the visual cylinder. So you can go to on the slide, and you can also change the orientation of the slide to see where you can see the most of your cylinder or the best view of your cylinder of the fiber. So I would just stick with the XY anyway, and then you can even actually rotate this slide here. Sometimes it's not really easy to look at one plane. You might rotate until you find the representative shape of your fiber in the easiest way, but I'll just stay with XY, give it rotate. And then just maybe go to this slide here and already see nice fiber. So now we're going to create the cylinder template to this data set. The way to create, you need to press the middle button of the mouse. So you position somewhere here. So you press middle mouse one time and you move the mouse away, and then that's the length of the cylinder. So you click the middle mouse view one more time and you create the template, the cylinder template. And you can click left to expand your cylinder. You can create a new one. For example, I create here and create a new cylinder by middle mouse click this. Or you can click here as well. And yeah, so I have to be careful not to, yes, like this. So you can just click the middle mouse view 2 times to create the cylinder in the position of your fiber that you see like this, and then start to expand the diameter until you see that the cylinder actually cover or fit the size of the fiber of the image. And you can see here, now I fit it here, and the outer cylinder radius parameter is being automatically detected and calculated. The same as mass cylinder radius also been automatically input, but still we also need to adjust the cylinder length again. So I said 4 to 5 times of these values. So 16, 15 to 20, or even 25, it doesn't hurt much to increase the size of the cylinder length. But don't put too long because it's gonna be not difficult. It's gonna be difficult to detect all the fiber. And the principle of this cylinder visual cylinder is that we're gonna run so-called the template matching using brute force. So imagine they're gonna run this cylinder throughout the full volume of this data here, and they try to correlate all the signal, bright or dark, that are fit into this shape of the cylinder. So run template matching brute force, and yeah, that's all. And we're gonna run cylinder correlation. Yes, they also have the option to do missing wedge correction. For example, if you run tomography, EM, and sometimes you also have this missing wedge, then you have to correct them with your tube angle. If you have information on your tube angle on the image acquisition in the EM, then you can just use this missing wedge collection as well. But here it's just CT, so yeah, don't have to be worried about it. So when I have all these parameter input, so you can see you can do manually. This will mean the diameter and get the outer cylinder radius and calculate the length by time 4 to 5. And or you can just use this visual cylinder template just to estimate and automatically detect this outer cylinder radius. And everything else use default parameter and click apply. So this is gonna take a little while if you have really low RAM memory and also GPU as well. So run, and imagine if you have any large data with a lot of fiber, it's gonna take why sometimes you can run an hour to calculate this. So what they do here, they want to calculate the correlation score. So from their very high contrast to low contrast. So what you can take a look, we have 2 results. One is correlation field, and orientation field. Correlation field is easier to see, to interpret. So it just gives you the correlation score from very correlated to the fiber that we match them. So the high intensity that more correlated to the template, and the low intensity is not very correlated. So it's look pretty much the shape of the fiber that we are looking at. Or you can add warrant to visualize this correlation field. by looking at the correlation in Warren like this. So as you can see, so most of the main fiber are in the high correlation, and the dim intensity is just not well correlated in terms of correlation score. But for the second result, orientation field, it's impossible for us to interpret by eye. So it's just some computing information to give the orientation of this fiber. So it really doesn't give you what exactly here, but we need it there. So, and one thing we need to understand is that because we work on the correlation score of the bright and dark and the contrast, we need to estimate the correlation score where we're gonna start detect where is correlation to be fiber or not. So for example, if you look at the dynamic range on the auto slide here, you can see that the maximum dynamic range is about 160, like it's around 140 to 160, something like this. This is where the highest intensity of the correlation score. And we're gonna use this information, the maximum number here, just estimate input number for the next step. So the next step we're gonna do is to do trace of this correlation line inside of this correlation field. So for example, here we have this correlation field like this, and we're gonna start tracing. We start tracing from the highest score. So we start from the inner part of each fiber by we find the starting point called seed point. So you can see that we can define seed point everywhere, but the seed point will be correlated to the highest correlation score, and then we start to define the seed cone angle. For example, you have for example, correlation view here, and when you start to define seed point anywhere here, and then we start to connect it, this seed point to become the fiber line. At this seed point, you have to define the search cone, the angle of the search cone, and the radius of the search cone, how far that you want to detect. So for example, we want to connect this line as straight fiber line. You have to define that it's not too high radius or high angle, because otherwise they will detect something here outside as well. Because if you have other fiber like this, for example, and you have also seed point here. So how can you detect other adjacent fiber? So you have to find it's called search cone, and this is called the angle and the length. It's very important that we can define that. And if you estimate it here, so you detect this one, and the next one you define the same. So you detect next one. So you just start to connect the seed point together on one correlation line. I hope it's okay. And then to do that, we need to attach the module called trace correlation line to the correlation field. Trace correlation line also in the X fiber tracing. So that two modules that are in X fiber that we need. So as I mentioned before, that in trace correlation line, the first thing we need to do, we need to define the minimum seed correlation. So this minimum seed correlation we can estimate, but it's not the true or the fixed value. So it's about this value 150, 160. So like estimate, because if you don't know the number, you might get the really low correlation score. So that means, for example, you have really low correlation score, you can pick up something that not the true fiber. So maybe you can pick up this around here as fiber, so they have really low correlation score. And if you set the correlation score too high, like 200 thing, then you might not pick up something that have not too high correlation score. You have to be in a range that they cover all this intensity from low to high. So that's why this number can give you a guideline what could be the optimum number to input for the time being. So I will use 160 as the minimum seed correlation. And when you get the first number of minimum seed correlation from estimate from this the maximum dynamic range of the auto site. The next one is minimum continuation line. So it's how much of the correlation score that you could continue in the same fiber line. Otherwise, it's gonna sprout, or you can just jump into the other fiber. So the minimum continuation is about half of this minimum seed correlation. So it's about 80. And direction coefficient. So if you want to have more straight line, so you go to very high. And if you want to have more, if you have more like curved or wavy fiber, then you have to reduce them. But here 0.3 is a good default parameter. Just leave it like this. And this minimum distance and minimum length is also, yeah, by default they detect it quite nicely. So the minimum distance is how much the distance between the two fiber that they allow. For example, if you look at these two fiber here, one here and one here. So this is the minimum distance between the two fiber, because if you put it too close to each other, and they will not, what can I say? They cannot detect both of them. And if you put the other way around, if you put too large minimum distance, then they will wrongly interpret these two fibers as one, because they are in the same distance. So you should be in kind of at least the distance that they can separate them each other. And also you can see that the minimum distance is still larger than the mass outer cylinder radius. Yeah, to give them at least space to tell them that at least are actually two fiber, not they are two fiber in one as one, not interpret them as one. And the length of the fiber. So here it depends on how much you want to detect. For example, if you don't want to have the short fiber, you can just increase the minimum length of the fiber. And then this search cone, what I just explained here so far. So you like have the imaginary cone, and then you have to define the length of the search cone, and also the angle. The length is the radius, the search cone radius, and the angle is just 37 is the optimum angle, should be do most of the job. And the minimum step between each cone, search cone, yeah, is about 10 steps. So this is usually the search cone parameter is already optimized by software already. So you just leave it as it. So mostly you need to input minimum seed correlation, half of minimum seed correlation. Half of minimum seed correlation is the minimum continuation, and then the rest is quite automatic detecting. If you not see the good result later, you can come back and try to adjust this parameter, and you see just like if you want to increase more line or reduce more line, then you can do this by clicking apply. You will get the results. Oh, yes, I missed one thing. You need to input the orientation field. So by look at the little white box here, you can see orientation field port just to connect it. So we need correlation field and orientation field as is mentioned here. So then click apply. Then really quickly, trace correlation line is pretty fast, and there's not much to do because they don't need to compute it brute force on data like say the correlation. So that's why it's much faster. So now what I'm going to do, I just visualize the result with the spacecraft view. Like this. So I visualize them, spacecraft view. You can see here, graph look pretty much the same as we see on the fiber. So you can, for example, node, you can change the node size and factor. You can also create and segment. You can select a line width, or you can change to tube and create a factor of the tube like this. So it looks pretty much correlated to my data, or even not warrant, but go to volume of the original data, rendering, and just put transparency like here, and spacecraft view change to, let's say, green like this, and maybe remove the node if you don't need them. Yes. and maybe reduce the node and change color to maybe yellow like this. And here you can see that it's quite pretty much all the fiber except the smallest one that we didn't, because we defined a minimum length, or the fiber that have small length will not be detected. You can also take a look on the table of the fiber that we generated. So we have here nodes, and each node you can click on it and you can just see node here. Where is it? Like this. You can see that they will highlight it, the node. Point, I don't think we can visualize all the point because it's too small. And because I also have this tube, so we can also change this line only, and then maybe like this. Maybe you can see point, but no, it's too small. And then to segment, you can just, oh yeah, you can see the point over here. When you click on each point, they will highlight where is the point that you are selected. But I don't think it's useful to really examine point by point. And then go to segment. You can also look at the segment by select segment that will highlight to you where the segment has been selected. Okay. And you can see in this the spatial graph view here, we have the information. But information we have here is not the real statistic shape of the fiber. It's just representative how long of this spatial graph, the curve length, orientation of the spatial graph, and for example, chord length. Everything is in the statistic of the spatial graph is not the real fiber information. But before we go further, I just want to show you a bit more. For example, if you go to node, I just inactivate them, and for segment, you can colorize them according. For example, you want to see curve length. That's possible because this spatial graph had dimension of the length of the spatial graph. You can also even increase the length or go to tube like this. So you can see that now you can visualize them in colorized. But if you want to, for example, look at the volume, the fiber graph of the spatial graph, it will not possible to visualize them because actually there's no volume information. It's just a representative line. So that's why you cannot have this. But if you would like to have the real information of the volume here, so then you need to do another operation. So we're gonna do it right now. So we need to segment them quickly. So using interactive thresholding. Interactive thresholding, and I segment the fiber as a label mask like this. Maybe yeah, it should be enough. Yeah, okay. So now I get what I get here is the label mask, and then I will calculate actually the real volume, orientation, surface area of each fiber based on this volume mask. So to do that, I just need to attach it's called fiber shape statistic. Fiber shape statistic here. And in fiber shape statistic, you need input is it the mask, which is this one, the mask. So I attach mask to this label image here. And also you need the original grayscale, which is the configured AM. And then you can also click to add a new spatial graph to generate new spatial graph. So by click apply, now you get the new spatial graph and statistic. And if you look quickly at this statistic here, this time you can see that we have even diameter of each fiber, area, volume, cross section. So this is the real statistic of the shape from the concrete. And now if you go back to the result of new spatial graph, visualize them with the same spatial graph view and look at it. And maybe I just remove this for the time being. So with the new spatial graph, you can see that I can change the segment length to, let's say, volume, and now it's possible. You can also tube scale with the mean radius like this as well, and then you can, yeah, not much mean radius, so something, let's say volume, the same thing. Too much. So chord length, let's say. Yeah. So now I colorize them, the segment color based on the volume. So the toward the red is more larger volume, and toward the blue is smaller volume. And the tube scale, so the smaller tube, that means they have shorter chord length, and the larger tube, that they have a higher chord length. So this is more like colorized and scale factor of the fiber. That's okay. So at this step, we can do something more on this. It's really interesting. So I just point this back to, let's say, line without tube like this, and I'm gonna convert this sequence graph here. You can change to maybe white, doesn't matter, like this. So this is original sequence graph. If you want to, for example, how can I make it easier? Let's say if I have this fiber here and you want to separate them to individual fiber, if you use normal separate object, I will show you quickly now. Separate objects. And even I try to maybe optimize them by using two here and then separate them. And the result, you will see that it's not very efficient in terms of separation of each fiber. Strange. So you can see that they cannot separate it very well. Even I try to use the minimum criteria of, yeah, it's difficult to really isolate because they are connected and they cannot really define which individual fiber. And how do we do this to separate into individual fiber based on the fiber that generate here from the spatial graph? So this is gonna come to help of the watershed segmentation again. So what we're gonna do now, we're gonna convert this spatial graph here into the markers for watershed segmentation. So we can select geometry to label, convert geometry to label. This module, we convert this spatial graph here into the label image. And then you can see you have to define the bounding box and the size of your image volume, but you don't have to define it. You can just add reference to your grayscale image here. Then this before, if remember, I didn't add any reference like this. Here you have a lot of information to input, like the bounding box size in X, Y, and Z. But if you just put this reference into grayscale, then you don't need to add any bounding box information anymore. And if I click apply, you can see that I didn't check the output, label output, and the output that I get here is just only the one label image, like this for blue. So you should also label the output, click label the output and click again. And now all the output will be labeled to individual label image like this. And now you can see that I can use this label image as markers for watershed segmentation of this binary mask that we created previously. So I hope you can imagine that how it's going to work. So here you can see the binary mask we create as mask and the label binaries that they are going to use as markers for the watershed segmentation. And now we are ready to run watershed segmentation inside mask. So you go to original grayscale data of the chocolate bar, this one, or not chocolate bar, the fiber, and you just attach the module called watershed segmentation, marker-based watershed segmentation in my marker-based watershed inside mask. A bit long here, watershed marker-based watershed inside mask. Okay, And in marker-based watershed inside math, we need 3 inputs. So the data is a grayscale concrete.am. So we need markers and binary image. So marker is this one, the one we just converted from spatial graph to label image and label them. So I just connect the markers port to this one, this the markers. And then we need to input the binary image. So the binary image is this one. Not this one, this one. So this is the binary image. So I need to connect the binary image mask to threshold. So we have grayscale, markers, and binary mask, and then click apply. So I get the result of the watershed segmentation that can look like this. So yeah, as you can see. Okay. So all of the fiber has been separated using the spatial graph as a criteria for separate them, so they can separate nicely. And maybe one last step before we finish. So if you would like to look at the interface between this contact of the label, you can also use label interface module called label interface. Label interfaces. And here you have to define number of faces. So let's say I want to have at least 3 faces contact to each other. It's gonna be difficult, but let's take a look. And you can get this contact face here. Look at the volume rendering of the contact face. So actually they don't have anything that are 3 faces are in contact. So just reduce to 2. Apply, and then you have this the contact between 2 faces. So if I look on original data like this, so this is where the 2 faces of the material are in contact. And if you reduce to 1 number of faces here, then everything that have 1 face contact, but yeah, almost everything. So mostly you just look at the 2 interface like this. So then you get the information of the contact face between the 2 labels. Or instead of grayscale, you can look at the actually the like this one. So here and this one. But I hope you see what I display. So yeah. Okay. Yeah, that's pretty much of everything today. And yeah. And since we are talking about this separation, so I have another example that would be really interesting, something really new. And also I put this example on the repository so you can try to use it. So what we're gonna do here, we're gonna add the let's say this one is the file called URHA27R. I already upload it on the link. You can download it and open it. And if you open the file, it's like this. It's mandibular bone of the stingray, and you can see the part of this bone they call tesseract. And the aim here, we want to separate them, and using normal separate object with watershed segmentation, sometimes it's difficult and not very good result that we obtain. So I'll show you quickly here. So I do interactive thresholding and look at 3D. Yeah, should be okay. Maybe even like this. Apply. And after that, just quickly separate objects. Again, this separate object apply watershed segmentation inside. So I try to separate as much as possible using one H maxima marker extend, and then connect the object and click apply. What you obtain from this separation would be something like this. And you can see that it's not really easy to separate them into individual objects. So what I'm gonna do now, I'm gonna use the new method called random wall distance map. So this can generate very nice result in terms of watershed segmentation. And I can also work on this segmentation in the image recipe designer, also very easy to see the result on the fly. Just to remind you again that how good of this. So first just need to load the data. The thing here should be okay like this. And I already created the workflow for this segmentation. So I just have to open the workflow, which is in this folder. Just give me one moment. Random box. Yeah. Recipe. So we have the recipe that we gonna apply a random walk distance map module into this. So I open again, because I just opened a new recipe, then they have to reset again. And you can see that the step that we are going to do here. First, we all add auto thresholding to threshold as I did before, and then apply random walk distance map. You will get as the distance map from random walk, and that's that. After that, we apply the watershed, and then we do the step change, and then we can subtract the watershed line from the previous images, and then label them, and then we can generate the result. So that let's see. So if I just load the data, and then you can see that they already fill in the recipe of the image recipe designer. So from the first step, we have the images here. So you go to auto thresholding, see that it just threshold everything on the high threshold. And then after that, we apply random walk distance map. And this distance map is better because previously, when we do watershed segmentation, we use chamfer distance map, but this time we create a new distance map called random walk distance map that give better separation. And then we apply this extrema watershed. You can see the watershed line where all the object will be splitted. So okay, then this line here. So this is where the watershed. And then from this step, we need to break and then make a new step change. So we gonna from the step 2 of this image from the watershed. When then we use the command called add not image or subtraction, and you can see now the step from the extrema here will be subtracted, and the object will be separated based on the watershed line. You can see here, like if you use normal watershed, they separate but not so correctly. They don't separate everything, but with the random walk distance map, then when you subtract the watershed line, better quality in terms of segmentation. And next step is just to label them. You can see here, after labeling, just only one step that we cannot separate it very well, but the rest is look pretty much better than normal watershed segmentation. And here we just need to expand label because we have the gap between each of the satellite. So expand them. You can see, yeah. And then just but when you expand the label, it's over segmented from the original data. So you just need to mask them. Then you have the actual data. And then you create label analysis just to extract information for each of the objects. So when I finish this, I just go to project workroom and then right click and select the image recipe player created and load that recipe again to run into the full data set. Let's say here, news, recipe random walk distance map. So ready and then apply. Yeah, so it runs on the bottom here, the process. It's not so long. Yes, and look at the data. I attach also like rendering. So you can get pretty much all the bone cells being separated. Much better than normal watershed segmentation. Yeah. I think this pretty much everything that we see so far. And yeah, if you have any questions, I know it's a lot to digest, but we have the recording as well. And any question you can also come to me and or write to us. Yes. Help answer the question. You think okay? Any more questions? Then thank you so much. I will stop recording. Ronel, are you here?
Yeah, thank you, Sarawuth.